We're going to do a demonstration of how to use the Vivado tools from Xilinx to simulate a Verilog design. We're going to sort of walk through the process here using a 32-bit adder design, briefly talk a little bit about the Verilog, but mostly focus on how to actually use the tool itself. So we're going to start here with the Start window. We're going to create a new project. And that's going to take you through a wizard to step through the process here. We're going to do this the simplest as possible. So we're going to provide a project name. For us, we're going to call this Adder32 Tutorial. The next step in the process is to choose the kind. We're going to do an RTL design. This would be for Verilog or VHDL type designs. We're going to keep this checked here. Do not specify sources at this time. We're going to add those sources later. We then need to choose the FPGA that we're going to use. We're going to choose an Arctic 7 FPGA. Specifically, we're going to use the one that's part of the Nexus 4 board, although you would choose the FPGA specific to your design. So we select the FPGA we want, and that's going to give us a quick summary of the project. We click Finish, and that will now take us into the main view of the project. So here's the main view that we get for the project here. Over on the left-hand side, we have the Flow Navigator. That's going to allow us to step through the various parts that we would want to be able to do the design. Just to give a quick rundown of what that is, there's the Project Manager where you can configure the settings. You can add new sources to the project. If you're integrating, generating IP blocks, blockrams, or various components that Xilinx provides, you can use the IP Integrator. We have the simulation here. This allows us to run simulation of our design, which we're going to focus on in this video tutorial. The other options we have are RTL analysis, synthesis, implementation, and program and debug. So these are the various steps that would be necessary to take our RTL design, analyze it. Synthesis will generate the underlying lookup tables and flip-flops necessary to implement that logic. Implementation will take care of the placing and routing for the specific FPGA that you're targeting. And then finally generating a bit stream and programming the hardware if you actually want to put this onto an FPGA. So we're going to start by adding some design sources. There's several ways you can add design sources. We'll just use the Flow Manager for now. We're going to add design sources. This will take us through a wizard. For us, we're going to add files. We already have these files that exist. We have an adder.32 and a testbench that we're going to add to our design. So we're going to select both of those, add this to our design, and then now they have added these designs to our system. Now over here you'll see the sources area. What you end up having in the sources, there's actually two separate areas where your sources will appear. One is design sources. These are meant to be the synthesizable sources for the actual design. You also have simulation sources, which correspond to those sources which are only used for simulation. In this case, the test bench is actually one of those components that's only used for simulation, but it's currently appearing in both the design sources and in the simulation sources. So we're going to modify this by clicking on that. That will show us down below some properties about that source file. And if we scroll down here, we can specify what the source file is used in. So for us, we only want it to be used in simulation. So not synthesis, not implementation, only for simulation. So once we've updated that, now under simulation, we're only going to see our test bench here, and under design sources, we'll see our adder here. So let's go ahead and take a look at our adder. If we double click that, it'll open up here. We can show the adder just to quickly step through what this adder is doing. It's a 32-bit adder. We've named it adder32. We have two inputs A, B, one output S. It'll be a 32-bit adder without a carry input or a carry output. So we're declaring A and B as 32-bit vector inputs. We're declaring S as a 32-bit vector output. And we're using an always procedure here to simply use a single statement to update our output S as the sum of A plus B. Pretty straightforward adder design. that we want to be able to actually simulate to show how we might do that. So to simulate this, we're going to then take a look at the test bench. And so now in our test bench, we have our test bench module. If you notice, the test bench itself doesn't have any inputs or outputs. Instead, what the test bench has is it has a set of reg variables and wires. The reg variables we're going to use those to connect to the inputs of the adder design, and we're going to be assigning test vectors to those inputs. And then the wires are going to be used to connect to the outputs of the adder design, because we're not assigning anything to the outputs, we're just observing what those are, so we're going to connect that to a signal. In our practice here, we have an _t for each of the signals. That's to help us differentiate the reg variables and the wires used in the test bench itself compared to the internal ports of the adder design. Next, we have the instantiation of the adder. So we have an adder32 component. The name of that component instance is adder32_0. And then in the port map assignment here, we're using a positional port map. We're connecting A sub t to the first input of the adder, B sub t to the second, and S sub t to the third port of the adder design. This will connect A sub t to A, B sub t to B, S sub t to S of the adder itself. And then we have our test vector process here. We're going to use an initial procedure where we're going to specify a set of test vectors for our design. The initial procedure only runs once at the beginning of simulation. So we're first going to have 3 vectors here. You really should have a lot more, but for illustrative purposes we only have 3. We're going to assign A to 5, B to 10, and then we're going to have some delay so we can actually observe what that output is. So this #1 tells us to wait for 1 time unit. The actual duration of the time unit is specified at the very beginning with the timescale directive here. So this tells us that each time unit is 1 nanosecond in duration. So we're going to assign A and B to the test vectors here, wait 1 nanosecond. Then we'll assign A to 50, B to 7, wait 1 nanosecond. And so on and so forth until we reach the end of our process here. So that's basically our test bench implementation. If we want to then run the simulation here, we have our adder32 test bench. That's the design itself that we're actually going to simulate because it's under simulation sources. So if we go to simulation here, we could look at simulation settings. Mainly the thing here is we're using the built-in Vivado simulator. If you have another simulator available, you can also use that. We're using the built-in one that Xilinx provides. And then we can simply click Run Behavioral Simulation. So this will take a little bit of while to create the necessary files to allow us to simulate the design. It'll end up opening up for us is a slightly different view of the system that will have a waveform showing us what those outputs are, and it'll show us the components in our design along with the inputs. So in the behavioral simulation view that we get here, we have our adder32 test bench that has signals A sub t, B sub t, S sub t. You can see the instance here called adder32.0, so you can use this over here to explore the hierarchy of the design. I'm going to go ahead and shrink this so we can see more of the other components for now. The second part here will show us the signals itself, and automatically any signals, any ports or inputs in your top level design get added to the waveform viewer off here to the side. So you can see they've already added to the design A sub t, B sub t, S sub t. Those are the only ones that we really want to focus on at the moment. So here's our window. We're going to go ahead and reset our simulation. By default it runs it for a certain length of time. I'm going to reset this back to the beginning so I have an empty waveform. I would also like to, for convenience, the default is to show these as binary values, but I'm going to select those, then I'm going to right click on this and go to radix, and we're going to change the radix to be an unsigned decimal, so we'll actually be able to see the values as decimal numbers. Then we're going to run this for just 5 nanoseconds. Again, we had a few test vectors. Each one only had a 1 nanosecond delay, so I only really need to run this for 5 nanoseconds, and that will then run it. And now I'm going to go ahead and I'm going to zoom out so I can see everything in my waveform window here. So you can see that we started off doing 5 plus 10, 50 plus 7, 0 plus 0, and then finally we had 1 million plus 34,991. So that's basically how we can simulate the design